Ладно. Okay, so today I'm going to talk a little bit. So it's kind of an offhand lecture. I must confess that I didn't have much time to prepare for it properly. So probably there will be lots of unproved results, and probably I'll stop shortly. But I'll try to. So today I'm going to talk about a few details which I totally missed about the Kontsevich construction. I will not definitely give you any proof of this construction because it's really very technical and it takes much time. But I just try to give few examples of how this construction works and what other related results can be obtained from this construction. So first of all, let me recall the formulation of Kontsevich result. Suppose you have a Poisson structure on Rd, a Euclidean space of dimension d, and pi is bivector. It can be a genuine bivector of whose rank changes depending on the point. Then Kontsevich constructed an infinity morphism U with coefficients Un from a space of polyvector fields on Rd with all this paraphernalia, with shift of dimensions and with formal variable h bar. But I'll omit them totally into a space of polydifferential operators on the same space with the same paraphernalia consisting of shift and formal variables. The construction was based on the following very elaborate construction. This theorem, this map is based on a rather elaborate construction. You consider various graphs which are represented by a set of points on the real line and set of points inside the upper half plane, and every point in the upper half plane has few arrows which exit this point. So these points are called vertices of the first type, and there will be vertices of the second type on the boundary, and all arrows will go from one point of the first type to another point of the first type, or from one point of the first type to a point of the second type. Doesn't matter. And and there are few restrictions on this graph which I omit. So this graph can be regarded as a kind of the pattern which you should follow when you take the composition of polyvector fields. Namely, we consider a labeling I of edges of this graph into the set of numbers from 1 to d. And so for every edge we know one label, and we put the operator d over dp, dxp, where p is the label which is associated to this arrow by this labeling, right? Then inside here we take the coefficients of the polyvector field, one of the polyvector fields we put here, and we take the coefficients which correspond to a set of labels which exit this vertex, and we apply this partial derivation to the coefficient and use this pattern to obtain differential operator, polydifferential operator applied to the points, to the functions f1 through fp. So that's more or less evident. This is something which everybody could have done, anybody, right? The most interesting part of this story are the coefficients w gamma, which are used to take this to when you sum up these differential operators, which you obtain in this way. So B gamma is a polydifferential operator you obtain in this way from polyvector fields. So every polyvector fields say so to say on the vertices, and then you just take this composition to obtain a polydifferential operator. So these coefficients W gamma, they appear in a very subtle way. They are obtained from the integration over a compactified configuration space, right? And the claim is that when you take un of gamma 1 through gamma n to be equal to the sum over all suitable graphs of W gamma times B gamma, then this map verifies the L-infinity morphism, the definition of L-infinity morphism. And the proof, as I explained, is based on pretty straightforward computations, because when you take the Hochschild differential applied to the polydifferential operator of this sort, and you can somehow use, so what is multiplication? Sorry, before I proceed, what is multiplication in this language, in language of graphs? Multiplication is the boundary, so the multiplication of the function f1, say, and f2 corresponds to the boundary component of the configuration space where these 2 points collapse. So when you send these 2 points to the same, you obtain a graph with 1 point less, and then you can, and that gives you a new configuration space, a component of the boundary of the configuration space, which I explained in the previous lecture. So when you use this Hochschild cohomology, it amounts to integrating over the boundary components corresponding to this kind of collapses, right? And similarly, when you take in a similar way, in a similar graph theoretic way, you can reinterpret the other terms on the right-hand side of the definition of L-infinity morphism. Let me recall that L-infinity morphism has this identity delta of un should be equal to the sum with sines of un minus 1 commutators inside here plus sum with coefficients with sines of commutator of up and uq. So all these terms can be reinterpreted in this way, right? For instance, this here amounts to the situation when your graph collapses into 2 distinct parts, one consisting of p points in the top, I mean the points of the first type collapse into two different sets. The first set contains p points, so to say, the other set contains q points, and it will give you this. And the commutator comes from the fact that there is not just one way to put these 2 new points on the plane, but there is a whole circle of the points which you can put depending on the mutual position of the points to which you collapse the groups of points. So this is how Kontsevich proved this theorem, and of course this is pretty technical, although very straightforward. There were other proofs which I mentioned last time, One of them is renowned Tamarkin's proof.
Sorry.
Yeah.
I ask a question. It all seems rather combinatorial
Yeah.
in some sense. Why do we need the upper half plane? Why do we need?
I think it's just a device which actually we don't need upper half plane. Upper half, Tamarkin's proof does not use this device at all. Tamarkin's proof is totally devoid of any combinatorics in it. It works with some, well, very abstract algebraic notions like operads, Cauchy duality of operads, and so on. And the only place where it uses something like that, one can call it a black box place, where it is where they actually recall the famous Etinghoff and Drinfeld result about Drinfeld. I think it's Etinghoff and somebody. I'm not sure about the second author. About Kazhdan-Etinghoff, yeah, precisely Kazhdan-Etinghoff result about the construction called Drinfeld associator. So Drinfeld associator is a way to construct a bialgebra from some very special kind of algebraic data. It's not very easy. It's actually based on some.
Some representation theory.
Yeah, it's representation theoretic more or less. But it's. I have once seen the way it was proved. It was proved on based on some very delicate. Actually, the proof of Kazhdan-Etinghoff result, the proof of the construction of Drinfeld associators actually involves the study of configuration spaces somehow. Somehow it still is there, but in very special way, totally different from this one. Because this Drinfeld associator, it comes from the study of so-called Zamolodchikov equation, which is more or less the equation which you can differential equation which you study on configuration space as far as I can.
It's a different kind of configuration.
Yeah, but yeah, sure, it's a different kind of configuration space, but somehow ideologically they're more or less clear. They're more or less close. That's what I can recall from very distant past. I have never actually studied this Etinghoff-Kazhdan construction. I just thought I knew it was there, and people just referred to it many times, and Tamarkin also referred to it, and that was enough. It's kind of black box. Except for this black box, Tamarkin's proof is totally devoid of all study of configuration spaces, right? But the way this configuration space appears is actually, I think I explained this last time, but very briefly in the end. So I'll try to do this now. Probably, again, very briefly, but I hope it will be, well, less briefly than yesterday, than last time. So let me use my notes, lest I would forget everything. Okay, here it is. Eventually, yeah, here we are. So there is a physical theory which is called Poisson sigma model. Let me give a few definitions now. So let X be a map from a two-dimensional disk. If you recall, which we got as just a space of a set of all complex numbers whose absolute value are less or equal to 1. Absolute value is less or equal to 1. Let's map from D2 into some manifold M. So there's a smooth manifold. And if we choose coordinates, say x1, xd, are local coordinates in M, then you can regard x as just x1 of u, xd of u. So you write it like this. Of course, this is only local. So let x be a map like this with these coordinates. U is a point in the disk. And we also consider a differential form, one form eta, on the disk, but with coefficients, with values in the pullback along x of the cotangent bundle of M. So when you have cotangent bundle, also can when you choose coordinates, you get basis in the cotangent bundle dx1 to dxd, right? So when you pull back this basis, it gives you a basis in this space, right? So you can write eta as in these local coordinates as eta1 of u, eta d of u, where eta I is just a differential form on d2. So we work in local coordinates, so there is no need to care about change of coordinates, right?
This means that we consider differential forms of coefficients in pullback of.
Yeah, in the pullback of a cotangent bundle. So there is this canonical basis associated with the local coordinates. So when you pull back this cotangent, you obtain a kind of
Differential forms with coefficients in differential forms.
yeah, right. You can it's a little bit
So
it's a little bit uneasy.
these functions must be how do you call it? Dependent, right?
No, actually, because actually, well, yeah, I use this basis just to identify this space with just the default default sum of the usual one forms on the disk. You see? That's the only purpose of introducing this, right? Actually, you can actually think about, well, if you like this, you can say that we have a pullback of cotangent bundle along the map, right? If you know what are pullbacks of bundles. So this bundle is trivial over the disk. So I choose the basis in this bundle, and this basis can be written down in this way. And then these eta 1 through eta n are just coordinate, kind of coefficients at this basis of the differential form.
So
Yeah.
in what way it can be base the space of one form?
So every eta I is a one form. Actually, eta I is the form eta I u of u d u mu. You see, there is only one complex coordinate though, but we actually don't care. Yeah, I can say that u mu is either u or u bar. It doesn't matter actually. Just pull back and you have this. That's very simple in this sense. So now for every such map x, every pair x and eta, the Poisson sigma model considers the action functional, which is equal to just the integral over the disk of the following form. You take eta I of u, which d xi of u, right? And also we assume that M is Poisson, and that gives us the second term. We add 1/2 of p of pi ij of x of u, eta I of u, eta j of U.
That is definition of S.
Sorry?
That is definition of S?
Yes. So just an integral of two form over two-dimensional disk. So this is one form, this is one form, this is one form, this is one form, and you take this combination. It is easy to write it down in terms of local coordinates, although I must confess I never thought about the invariant meaning of this functional. It looks pretty crazy to me, to be sure. You just pull back differential forms, you pull back the coefficients of bivector field, even though it's not very well defined. The pullback of bivector field is not well defined. You cannot pull back vector fields along maps, right? But coefficients, well, there is no problem. And then you take differential forms, couple them with coefficients of bivector fields, that's a gain. So it's kind of value of bivector field on this differential form, but yeah, this differential form lives on disk. And that, so anyway, it's more or less. You can give some invariant meaning to this, but it's not that evident.
J is one form.
Yeah, there are one forms on the disk, right?
With coefficients in another.
Yeah.
In another forms, yes. And
Yeah, actually, so you take wedge product on the disk. You take wedge product on the disk. That's what you do. Right. So actually, again, you see, pi ij's are coefficients of polyvector field, bivector fields. So the way they transform when they change coordinates in the space M, in the target space M is called target space. They transform in a covariant way, right? And eta I are coefficients at the differential forms on M again, so they transform in a contravariant way when you change coordinates in M. So in total, you get something well defined here, not independent on the choice of coordinates, but still, it's I still don't see the meaning, the invariant meaning of this construction. Okay, anyway, we had this, but that's not the craziest part of the story, because actually we can now define the star product of functions on M. So let f and g be two smooth functions on M. And then you define the star product of f and g as a function which at point x takes the following value. You take a map x from this set, and you assume that, so the boundary of the disk, so you identify the boundary of the disk, D2, with the boundary of upper half plane actually. It's standard thing in physics. When you identify when you take what you call so it depends on how you define this. You can do the following trick. You can actually first there are two ways you can look at this. You can either identify the disk with the upper half sphere of Riemannian half sphere, upper Riemannian half sphere, right? You can use, for instance, stereographic projection to get this identification, right? Then this upper half sphere, so since a Riemannian sphere is nothing more than just a compactification of the complex numbers, so this upper half sphere, you can identify it with half plane. And on the boundary of this half plane, there are 3 points, three marked points: 0, 1, and infinity. Right? So we can see that the maps which send infinity to the point x. So point x is in M. So functions f and g are functions on M, so you take this map. Then you take f of x at 1 take g of x at 0, take, I'm sorry, I need to erase this, sorry, I'm running out of space. Anyway, and you take the exponent of 1 over h bar of the action functional s of x and eta, right? And then you take the integral over the space of all maps with this property.
It's just smooth maps.
Just smooth maps, all smooth maps of this property, and all etas with just additional condition that eta u applied to psi is equal to 0 for all u at the boundary, sorry, dg2, and all psi tangent to the boundary. So this is one form, so you can take the vector, yeah, take the vector tangent to the boundary, and then you use this in condition. So this is, so you integrate over dx d eta. As you see, this is not a well-defined thing, of course, because you have to integrate over infinite dimensional space, and not even nonlinear infinite dimensional space, because the space of maps into a manifold is nonlinear unless your manifold is just Euclidean space, right? However, if you believe that this map is well defined, if you believe that this integral is well defined, then you can prove that this product is actually associative. If you believe that this is well defined, then the associativity of this product is an easy exercise. Namely, we just write down the associativity condition. It is that f star g star h is equal to the other way around, f star g star h. On the other hand, this first term is equal to the integral, the double integral. So first we integrate over all x which tend infinity to x f x of 1, right? Right. Okay, great. And then we multiplied by the value of, say, g star h at the point x of 0, right? And what is this? It is equal to the integral over all y which tend infinity to x of 0, right, of g of y of 1, h of y of 0. And here we have dy, d, I don't know, d eta, I don't know other Greek letters, eta twiddle, let it be. And you again need to integrate this over dx, d eta. So this is what you have to insert there, right? So what is this integral? Suppose we are able to change the order of integration. Of course, I don't know what is this integral, but we assume that all the good things about integrals hold true for this mysterious integral.
And they actually hold?
Actually, you can make them hold. Actually, there is no definition. The definition of this integral is actually pretty involved. You cannot define it using the standard measure theory. It is impossible.
Isn't it just kind of the path integral?
Yeah, it's kind of you can regard this formula as a kind of mnemonic rule, actually. The way, there is a very pretty rigorous way to unravel all the definitions of this integral. And this, if you unravel all the definitions using so-called BRST and BV and all the formulas, you would obtain, people say so, Catanel and Felter say so, you obtain precisely the formula by Kancevich. But now, if you just forget about this rigorous way to unravel all the definitions, you can do the following easy trick. Look at this integral here. If you take this integral, so let me draw the disk x, the disk which is mapped by x. There are 3 points at this disk. One point is infinity at the boundary of this. One point is infinity. The other point is x1, or is 1, and the third point is 0, right? Now, this disk is mapped by x to the target space. Now we have another disk mapped by y to the target space. This other disk also has 3 marked points on the boundary. It has infinity, it has 1, sorry. So I need to keep the orientation. So they go in clockwise direction. So we have 1 and you have 0, right? So somehow you need to take this kind of product, this kind of batch, a bouquet of 2 disks, right? We can look at this as a kind of cactus. And you need to integrate all possible maps of this configuration into the target space, right? So this actually integration is just integration over all maps of this construction into the target space. Of course, this construction topologically is the same as just one disk, where we have 1, 2, 3, 4, 5 points. So one point, so we actually just kind of split this point into 2.
After we passed from iterated integral to double integral.
Yeah. So actually, we actually can forget about this point. We can just kind of topologically, this disk is just one disk with 1, 2, 3, 4 points on it, right? So infinity first infinity, second 1, second 1, and finally we have 0 bar. Have 4 points. You need to integrate over all maps which send this point to x, right? And we need to integrate over all possible positions of these points, more or less, right? But if you take this construction, it would also be equal to the integral over the same kind of configuration. Because here you will have a circle, actually the disk, which corresponds to H, right? Where you need to fix the point, need to send the point 0 to the fixed point, I don't know, to some point, I don't care about this now, right? And then you add the disk which corresponds to this star product. And it will be topologically equal to the same disk again. So if you unravel all the definitions, that's actually all what is important for the proof of associativity. It is just a topological consideration which says that disk of this sort, this kind of configuration of 2 disks, is equivalent to the configuration of the sort where we glue this disk in a different way, a little bit. If you want, I can unravel this for you right now. You can begin with this. Let me erase it. So you have equal to the integral of f star g x at the point x of 1, right, times h of x of 0. Here we have integration over all x which is an infinity to the point x. Now this is equal to the integral over all y's which send infinity to the point x of 1, right? And then you get f of y of 1, g of y of 0. And if you write it down, you get a configuration of this sort. You get a disk mapped by y, where you put f at the point which corresponds to 1, f here, then you put g at the point which corresponds to 0, and then you glue another disk, y infinity is equal to x of 1, where you have, here you have 1, here you have 0, just let me see, infinity 0, 1 should go in a clockwise direction, infinity 1, 0. So here we have infinity 1, 0. That's correct. Here we have 1, here we have 0, and we have infinity. Right? Infinity goes to what? Infinity goes to x. So this is meant by x. And 0 goes to h. So if you again uncouple this point and get a single disk topologically, there will be again 1, 2, 3, 4 points. This point goes to x. Here we put h. Here we put g. And here we put f. And we integrate over all maps which send this point to x. And we put f, g, and h into these 3 points on the boundary. And more or less the same we have here, because here we have f here, 1 bar we have g, and here we have h. So f, g, h in the same clockwise direction, right? So we have the same configuration, we have integral over the same configuration with the same maps, with the same properties, and of course it is natural to say that these two integrals just give you just the same thing. So this is how the star product is restored. And if you want to restore it in its full glory, that is to say with all, and of course I omit all the coefficients here. There is this weight which says there you have exponent to the I divided by h bar, s, and so on. Of course I omit this. Yeah. And of course it is necessary to show that the weight you obtain in this way will be equal to the sum of the weights. The weight here will be equal to the sum of the weights here and here, but that's more or less evident because when you integrate over this configuration, it's just the same as you integrate the induced function over this configuration. That's almost clear. That's much easier because this involves only finite integration over disk. So this gives you the associativity on the nose. But to make this, restore the star product in full glory, you need to do the lots of exercises here, lots of kind of work. You need to use Feynman diagram techniques to replace the integral by the sum of graphs of certain finite dimensional integrals, and then you need to check that the graphs you obtain are precisely the graphs that you obtain from the Kontsevich construction and so on and so forth. That's not easy.
It's kind of the path integral quantization.
Yes, precisely. It's path integral. But you see, the problem is that in path integral you actually have this integral. You believe that the inset integral is equal to something. So since mathematicians do not believe in such things, Kontsevich had to erase the integral totally from the considerations. And just the only thing which survived looked very mathematically rigorous. Okay, that was the first part of today's story. The second part was I tried to formulate and probably describe in some detail the proof of Duflo formula, which is due to Kontsevich. It's actually been proved not by Kontsevich, but rather by Van den Berg and Kalak later. But the construction itself was contained in Kontsevich theorem, so I think it's better to call it this way. So let me first explain you what is Duflo theorem. Suppose you have a Lie algebra, and as I explained a few months ago, the Lie algebra, or rather its dual, is a basic example of Poisson manifold. So if you take G star, then there is a Poisson bivector, canonical Poisson bivector at this G star. Namely, you just reinterpret the Lie bracket on G as the Poisson structure. Or more accurately, elements of G are going to be regarded as linear functions on G star by duality. So you have two linear functions on G star, then you say that their Poisson bracket is equal to their Lie bracket. Right? So this is a linear function, this is a linear function, and this is also a linear function. This also belongs to G. Right? So you get this, and then you use Leibniz rule to extend this construction from linear functions to any functions, to any smooth functions. Yeah.
Actually, for the smooth functions, you need to consider the tangent space, not only Leibniz rules.
Sorry, what else?
You need to identify the tangent space of G star to G itself.
You can do this actually, but I think it is enough to have Leibniz rule, because actually, if you have Leibniz rule, suppose you have again, suppose you have just a linear function and you have any function at all, right? Then by Leibniz rule, this is equal to, this is a derivation, right? So if you know how to derive linear functions, then of course you know how to derive any functions. Of course there is lots of details you can use, but if you have a derivation and you know how to apply this derivation to linear functions, you actually know how to apply this derivation to any function at all, right? But yeah, you might prefer to be more specific about details, but I think details can be omitted for a while. Yeah. Okay, so we have this. We have Poisson structure, and one can apply. So of course, G star topologically and even geometrically is just RD to some power D. So we can apply Kontsevich construction directly to here without any globalization. Of course, in general case, you need globalization procedure, which I omitted last time. I only sketched it in the parentheses after the lecture. But here we have Kontsevich construction on the nose. So this construction gives us a star product on the space of all smooth functions of G star, right, with this H bar inserted. And it is easy to see, I think I explained this to Dejan when we talked yesterday, that this star product sends polynomials to polynomials, actually. So if you have two polynomials, f and g, so polynomial functions on G star, you can regard it as a polynomial of linear functions. So since we identified linear functions with G, we can actually identify polynomial functions with symmetric algebra of G, right? So we take these polynomials, and then if we take f star G, it will also belong to S of G with H bar. So why? Well, it is not easy, not hard to see, but to this end you really need to. So it's actually worse than that. You can actually show that you don't even need infinite sums here. So to see this, you just need to look a little bit more attentively at the diagrams which appear in Kontsevich formula when you substitute this type of bivector fields into Kontsevich formula. Let me recall this, that this bivector, it is actually linear. In local coordinates, it is written as xk ckij di dj, right? In local coordinates. I think I wrote this in local coordinates. So all coefficients of this bivector are linear in the coordinates, right, in terms of coordinates. So you cannot differentiate it more than just one time. If you differentiate it twice, it will vanish. Now look at the diagrams which appear when you use and you construct un of pi, pi, pi. All these diagrams will be of this sort. So first of all, there will be only 2 points of the second type. So because you obtain a bivector, right, eventually. Next, there will be n points of the first type, and every point will have exactly 2 arrows leaving this point. In total, there will be 2n arrows leaving points. But how many end points should these arrows have? Of course, there should be 2n endpoints, right? But only n of these endpoints can be in the vertices of the first type. Because as soon as you get points, 2 arrows entering the same vertex, you get 0. Because then you have double derivations, second derivation of second order of the coefficient. And this coefficient is linear. So there will be only no more than n arrows getting into this point, right? Into the points of this sort. So there will be n arrows which enter these 2 points. So the degree of this bidifferential operator, the total degree, will grow with growth of as n grows. Will grow at least, it will equal at least to n. And when you apply a differential operator of growing order to polynomials, it will, first of all, it will give you a polynomial again, right? And second, it will, as soon as the degree of this bidifferential operator is greater than the sum of degrees of f and g, it will vanish. And this can actually gives us this simple observation, right? Next. Right.
I'm sorry. Can you remind the operation? How do you deal with these graphs? What do you like operationally?
Again, so the idea is very simple. You put bivector at every vertex of the first type. You put functions f and g in these two vertices. Then you draw the graph. When you have an arrow, it means that you take one of the partial derivations and apply it to the entity standing here. And then you just take the composition of this sort, and that's all. By the way, just enumerating all the graphs of this sort is already quite an interesting question, by the way. If you look at the graphs attentively, you will see that there will be two types of graphs. One type doesn't have cycles. It looks like this. So that's the graph of the first type. But then there will also be graphs of the second type with cycles. They are called wheels. Right? So, and all the other arrows which exit these vertices, they'll go to the points of the second type. So you have wheels and you'll have this. And one of the interesting results is that you cannot have universal formula without wheels. A formula which would work for any Lie algebra, for any Poisson manifold. But in fact, you can construct a formula for this, for the star product for universal enveloping algebra. Sorry, for this type of algebra, without wheels. But yeah, it is possible. It is possible to draw to construct the star product such that all the operations will be given by this kind of graphs, and all the wheels will be removed. But this formula will not be universal.
So then it is not just as a Kontsevich structure. It's not a.
Well, of course, Kontsevich gives you just one of the possible ways to construct this star product. It's just one of the possible ways. There exist infinitely many ways to do this. Actually, they will all be equivalent in some sense. If you, well, up to the identity. So if you take this equivalence relation of the star products, so these star products will be equivalent, but the formulas will be different. You see, that's that's a pretty subtle thing. So anyway, you have this, and it gives you the star product just on this kind of algebra, right? You have star product here. And if you take, so of course, G itself is inside this algebra, and you take the element x and y in G, and you take their star product and take the commutator with respect to the star product, you will obtain h bar times the commutator of x and y in the algebra. And this means that there is a map from this algebra with this product to the universal enveloping algebra enlarged by adding this formal variable h bar. So there's a map from this algebra into universal enveloping with H bar.
I'm sorry. Why did high terms cancel?
They're not cancelled because all other, if you look at this formula, you'll see that all the differential operators of the will be of the higher degree.
X and Y is just linear.
Yeah, just linear.
So the high terms will
Yeah.
vanish.
High terms will vanish.
So when you take x, I see.
Yeah, yeah. All high terms will vanish. Actually, there will be two operators which potentially give you non-trivial element out of two linear maps. This one and this one. But this one gives you some symmetric, so it will cancel out. You see, this part will give you symmetric part. So it will cancel out when you pass to the commutator. It's not quite straightforward. It's all a little bit involved. Okay. Anyway, we have this. And of course, if you look at the induction, if you work by induction, by dimension, so on, you know that according to the to the Poisson-Birkhoff theorem, this algebra is linearly isomorphic to this algebra, and this means that you can now elaborate this observation to obtain isomorphism of these two algebras. Sorry? Associative algebra isomorphism.
Really?
Yeah.
The star product corresponds to the tensor product here?
Not tensor product, the product here. You have a very well-defined product. This is associative algebra.
Yes, but it's just a tensor product modulus.
Yeah, precisely. Yeah. Yeah, but you can show that this is the same.
You can only see the Lie brackets are the same from here, but not the.
But this algebra has a universal property that whenever there is an algebra which contains G,
I see.
such that the commutator is equal to the Lie bracket, then there is a map from here to here. And then you can use just the kind of dimension counting to identify, to get this identification.
But probably it's better to write star.
Maybe the map is in the opposite direction, by the way. I'm sorry. The map is in opposite direction. I'm sorry.
Well, I mean, it's better to put stars there.
Where?
On the left.
Star product? I mean the star? Well, I'm sorry, but I'm running out of space. So in any case, you see this is related to the universal enveloping algebra. Now, it is one of the advantages of Kontsevich construction, I mean, of the advantage of all this business with an infinity maps is that it allows you to do a little bit more than just construct star product. It actually allows you to transfer a little bit of structure from the Poisson side to the associative side. One of the structures is the center. Let me recall you that if you have a Poisson algebra, the algebra of functions in Poisson manifold, or just an algebra with Poisson bracket, and the Poisson center of this algebra is just the space, a set of all functions f in C infinity of m, such that the bracket, the Poisson bracket of f with anything else is equal to 0. Speaking a little bit in a more refined way, you can regard the the Schouten bracket with a Poisson bivector. So if you have a polyvector P and you have a Poisson bivector pi, then taking the Schouten bracket of P and pi, you can regard it as a kind of new differential in polyvector fields, in the space of polyvector fields. This actually is easy to see that d pi squared is equal to 0 if and only if phi is Poisson, right? Now, if you look at the general theory of Maurer-Cartan elements, so suppose you have a Lie algebra, differential graded Lie algebra G. So this is not that Lie algebra, this is differential graded Lie algebra. Recall that the Maurer-Cartan element phi is an element of degree 1 in G, such that it verifies the condition d phi plus 1/2 phi comma phi is equal to 0. Let us consider consider the map. Consider the map d phi from G to G, given by d phi of psi is equal to d psi plus phi comma psi. Write down d phi square of psi. It is equal, first of all, to d phi d square, it is 0, and you apply d here.
So what's the d? What's the differential on G?
Sorry?
The d. What's the
I told you that you can see the differential graded Lie algebra. So there is some inherent differential, just part of the structure. It is not that I told you that's not this old Lie algebra. I'm just speaking about a little bit different things now. But unfortunately, I don't have enough letters to employ. I'm sorry.
So this process G is a differential.
Yeah, now I suppose for a while that G is differential graded Lie algebra. This is part of Kontsevich theorem, actually. So d square of G of psi is equal, here we have 0, then we have d phi sub psi, comma psi, minus phi d psi. That's when we apply d here, but then we also need to apply this. This gives us phi phi d psi, right? Plus phi comma psi. So these two terms cancel out at once. Now this term, according to the Jacobi identity, is equal to 1/2 of phi comma phi commuted with psi. Now if we add the first term to it, and recall that phi is a Maurer-Cartan element, we see that it actually vanishes. So it means that we have a differential, a modified differential. Just like here we had this modified differential, you recall that we used to consider 0 differential on polyvector fields, and now when we have Maurer-Cartan element on vector fields, on polyvector fields, we can modify this differential by adding this term, right? And just like this, we can do the same thing for arbitrary Maurer-Cartan element on arbitrary differential graded Lie algebra. Now, Kontsevich theorem was based on the following Conceived result, not the theorem, that theorem is much deeper. Conceived result was based on the following observation, namely, the application of Conceived theorem to the deformation quantization business was based on the following observation, that if you have an L infinity map F from G dot to H dot, when G and H are two differential graded Lie algebras, then F of pi equal to, sorry, F of phi, let phi be a Maurer-Cartan element, equal to the sum 1 over n factorial f, let it be fn of pi, sorry, phi, phi, is also a Maurer-Cartan element. Right? It turns out that it's not just this which is true. It is also true that you can extend this map in such a way that it will intertwine the new differentials. Namely, if you consider the map, let me recall it, let me try to remember this. If you have a map, F, and you can also consider the map F sub pi, which will also be an L infinity map. But this time, F sub pi, comma n, applied to G1 through Gn will be equal to the sum 1 over n factorial F, 1 over k factorial, n plus k, G1, Gn, and then you'll have pi, pi, k times. It turns out that this is an L infinity map between G endowed with this two differential d sub phi and H endowed with the differential d sub f of phi. Right? It is a straightforward result, and it is proved precisely in the way we proved that this is again a Maurer-Cartan element. So just do the exercise working with the definition of Maurer-Cartan elements and of L infinity maps. And that's all. Oh, sorry, you're right. I should have written phi. Yeah. Phi is a generic Maurer-Cartan element. Yeah. And pi used to be just a bivector. And bivector plays precisely the role of Maurer-Cartan element. And now you can use this observation. Kontsevich calls this the tangent map associated with the L infinity map. And it gives you the following result. If you take this tangent map, U sub pi, this also should be U sub phi, so F sub phi. I'm sorry for this. There are too many repetitions. So now we have Kontsevich map from polyvector fields to polydifferential operators, and you apply this construction, and it gives you map from polyvector fields with this Poisson differential to polydifferential operators. with this d sub b probably. Now let us apply this associative, this kind of tangent map to the case when we take just one.
Tangent map is called the sum.
Yeah, this map is called the tangent map. It is actually an infinity map from this to this with new differentials.
Ah, okay.
So now let us take u pi comma 1 and apply it just to function f. Right? It will give us again, by if you count the degrees, it will also give you a function, or rather a series of functions with h bar times functions. It will be c infinity of m of r d, I don't know. Right? I have this. But now if d pi of f is equal to 0, it means that d sub b of, sorry? It is zero vector field. It has zero vector field. This is, yeah, polyvector in the sense of, has zero vectors inside. But it's also a polyvector. By this formula. You just substitute pi instead of phi, that's all.
Ah, okay. And u is cancellation.
Yeah. So now what it means that d pi of phi is equal to 0? It means precisely that f commutes with everything. And this here, I leave it as an exercise to you. It is easy to show that this map actually means that u pi of f commutes with everything in the sense of star product. So this map u pi 1 sends the center into the center, right? Nice. Now, what is the center of universal enveloping algebra? And what is the center, the Poisson center of S of G? It is actually not difficult to show that it is equal to the space of add G invariant functions, where G is the connected Lie group with Lie algebra G. Suppose we work over real or complex numbers, then there is this is well defined. This integration, you can integrate every Lie algebra in this case to a Lie group, and then this gives you this result. Right? Nice. So we are almost there. So let me explain why this is so. Actually, an element here commutes with an element with everything. F G is equal to 0 for all G, if and only if F commutes with all linear functions. Right? Since we work over polynomials, it is enough to consider only this, right? Now, if you work here, look here attentively, you'll see that this commutator, this Poisson, is equal precisely to the differential d over dt at t equal to 0 of the following thing. You take f, so it's at a certain point, I don't know, y. Exponent, take exponent of tx, take a joint action over this exponent applied to y. Rather a joint, dual joint action, right? So you have this is equal to 0. It means that this is equal to f of y for all t. So since and the result follows automatically. And now the same is true for this center, and the proof is precisely the same. I just check that the commutator with an element in the Lie algebra amounts to taking the adjoint action over the Lie algebra, so then you integrate this adjoint action to the adjoint action of the group, and then you obtain the same result, that this is equal to the space of G invariant FG invariant part of this algebra, right? Nice, right? And of course, it is interesting to see if so. Of course, so they are linearly isomorphic. These two spaces are linearly isomorphic. And actually, the map, which the standard symmetrization map, sends this space into this, just because it intertwines the action of the Lie group. It commutes with the action of Lie group, so it sends this center into this center. However, this anti-symmetrization map does not commute with the product. So this linear isomorphism is not an isomorphism of algebras. So it turns out, however, that this map is an isomorphism of algebras. And the proof is based on the additional properties of the Kontsevich map. Kontsevich map, in addition to being just L infinity, to respecting the L infinity conditions, it also respects the additional condition, the additional structure which is there. The additional structure on Hochschild complex is the cup product, and the additional structure on polyvector fields is wedge product. So one can show that U, the Kontsevich map, well, I wouldn't say that it intertwines the cup product with the wedge product with the cup product, but it does so up to the differential. You can do this like this. So U1 of, say, P wedge Q is equal, U1 comma phi, right? U1 comma 1 comma pi is equal to U1 comma pi of P cup with U1 comma pi of Q plus differential of something. That's what you can prove. Now it follows from, now if you count the degrees, the dimensions, you will see that these extra terms disappears when you work with functions, right? Yeah, I think this is it, more or less. Let me see if I'm not telling you some total nonsense. Okay, I might be a little bit hasty here. I'm just in a hurry to finish this talk, so a little bit hasty. Actually, let me take a look at my notes. Yeah. Actually, yeah, it's not. Yeah, I think it is this. I think it is more or less this. I told this correctly. There should be this homotopy between these two. Yeah. Yeah, that's it, more or less. Yeah. I mean, of course, the problem that this vanishes only when df dp is equal to dq is equal to 0. Yeah, I'm sorry, I had to say this. d pi. Right? Yeah.
Q is just functions, yes?
Yeah, if p and q are functions, then and both p and q vanish under this differential. So if they are central, Poisson central, and this additional term will disappear, will vanish. It follows from the from this condition and from the dimensions count. The only term which could appear here should depend on differentials of p and q, and they vanish. So if you look here now, you will see that means precisely that Kontsevich construction sends not just sends the center into the center, but it sends it as algebra. And you can actually unravel the definitions further, and even can compute the coefficients of this map. And it is, if you do this, you obtain pretty interesting result. I'm not going to prove this. The result you obtain will be precisely the Duflo formula. If you have heard about this, Duflo is an older construction which gives you an algebraic isomorphism between this and this, independent on the choice of generators in both algebras. Just an abstract way to draw this isomorphism. And here's another isomorphism, which appears automatically from the construction. Unlike Duflo, which was based on an elaborate study of Kirillov integrals of orbit spaces, of orbits, this comes absolutely naturally just from the algebra L infinity morphism with additional property. And yeah, and the fact that you can actually compute the coefficients is even more interesting in my opinion. But yeah, I'm not going to talk about the coefficients now. I'm running out of time. I think it's better to stop here now. Okay. So yeah, before we proceed. So next time we shall have a break, because next time there will be some important business at our department at Moscow University. We shall be actually kind of, we will be alluring, we'll be trying to allure prospective students to our department in Moscow State University. So the next time we shall miss this, we shall not meet or shall not convene. And on the 5th of April, I already arranged a talk by a person from Dubna, and he will speak about Manin's matrices. There are two aspects of this. So first of all, Manin matrices are matrices of non-commutative algebras with non-commutative entries, but such matrices where you can somehow define the determinant of these matrices in a more or less consistent way, right? So he will talk about this, about the way they are used in applications, I hope. And then there is another way he will talk about this. He will also explain some categorical construction which lurks behind the definition of Manin matrices. It turns out that Manin matrices can be interpreted in a categorical way as morphisms in certain category. I hope he will explain this to us. Okay, so see you in 2 weeks. Okay.
How many other
Huh?
results of conservative?
Sorry?
How many other results of conservative?
You mean what? Here or in general? There are lots of them.
In general.
In general, there are lots of them, but I'm just talking about one. We're just talking about one theorem, which is central for the deformation theory. There are also some results of his in, let me see, how they call it, in integrable systems, in theoretical physics. Alexander Kontsevich, I don't forget the S. Somebody, and Zaboronsky. There's also Schwarz-Zaboronsky, AKSZ. There are also results in knot theory, so-called Kontsevich's universal formula for Vasilyev invariance. There are also some recent developments in what they call the mirror symmetry theory and so on. So plenty. It's not our purpose to study all his results. It's a purpose to study just one, but into some depth, I'd say.
So what about Kontsevich's just the deformation theory?
I told you that this is central. This central result, the formality theorem. It is central for it is the existence theorem, and the construction. Since this L-infinity map is so nice. There are different L-infinity maps which were constructed by other people as well, but this particular L-infinity map is so nice it actually intertwines the cup product and wedge product, and that's also important. Okay. Okay, let's go on next time, continue next time. So, what? Are you tired? It seems to be. Okay. Seem to be tired.